So we're going to consider the seed, the three-dimensional seed, and the triple um, I3 is the geometric carrier, geometric scaffolding, orbifold sheet geometry. Gamma is the seam graph, and pi is the finite symmetry group. So let's choose a finite set of distinct points in R3. We could choose those P1, P2, P3 for example, for a k equals 3 case. And instead of deleting the points only, we will basically take these closed balls, uh, disjoint, and which are centered at the points P sub I, and basically delete them from the surrounding R3. Then you get a smooth three manifold with boundary with these balls. So we get the points resolved into spheres of directions. We can see MP as the real oriented blow up of R3 at the finite set P. Now we're going to enrich each exceptional sphere by a copy of the three-dimensional seed, denote it as such. And so we get this boundary of seeds. So we have this R3 and it's collapsing to this boundary of disjoint seeds. Now, for each I, let U sub I be the collar neighborhood of the boundary component, um, boundary of BI. We get a, a radial strong deformation retraction, which can be given by the following. And if we equip the boundary BI with the seed structure, then we can interpret this as a local seed collapse map. So we're basically collapsing this R3 onto the outer boundary of the seed. We might not, in general, expect a global deformation retraction because MP is connected, whereas the target is disconnected. If you want a connected seed scaffold, you can choose an embedded tree where the endpoints meet the K boundary components, and then you can take the connected seed complex as follows. Now we're going to act on these seeds with symmetry groups. We're going to choose an oriented orthonormal frame at each point pi, and take a element of the SO3 rotation group. So we're going to rotate these seed boundary components, which will twist around the ambient geometry of R3. We'll also take pi, an internal symmetry group pi3, which is like a piecewise isometry group acting on the internal geometry of the seeds themselves. So the SO3 group rotates the entire embedded seed while the pi3 acts through these piecewise isometric deformations of the seed itself. So you got these um, independently rotating seeds and parameterized by this R equals the tuple, the K tuple is an element of SO3K. So a basic geometric question is how the surrounding Euclidean geometry responds to a path of seed rotations. In particular, we're going to look at holonomy with respect to this question. So one way to formalize this is to introduce a geometric field or connection, AR, on the complement, MP, subject to the boundary conditions determined by the rotated seeds. So we want to basically understand how this these actions of these seeds twist their surrounding ambient geometry, and how this interacts with the spin-3 group and holonomy. So we're just looking at spinors here, and you can a nice visual is the belt trick or the ribbons attached to a rotating ball visualization there. So if we think of the state attached to the ith seed transforming under spin representation, then we can have these maps respectively. This is the hallmark structure of a spinor rotation or spinor. Needs 2 rotations to come back to its original orientation. So we have these two actions: the spin-3 frame acting on the cover of the seed, the 3 seed, and the pi group action on the 3 seed cover of the 3 seed. So the problem that is interesting to me is, given k seed-enriched point defects in R3, determine how independent paths in SO3K together with the intrinsic pi 3 actions generate holonomy in the surrounding space, and whether this holonomy admits a natural lift. In this formulation, the objects S3 behave as frame geometric defects. The ambient rotations produce twisting data in the complement. The spinorial lifts distinguish a 2 pi rotation from a 4 pi rotation.